Okay, so today's lesson is all about waves. We've been studying about energy in different ways. We've been studying about the different forms of energy, the different states of energy, potential and kinetic. And then the last week or so, we've been talking about heat and moving heat and thermal energy. And these are all related to energy. And now we're going to move on and talk about waves because waves carry energy. So this is a related topic. To start with, let's talk about what a wave is. And here's I guess a textbook definition of what a wave is. It's a disturbance that travels through matter or it can travel through empty space. And of course, we're talking about energy. It carries energy. One of the things that I need you to understand is that it is not matter. Okay, it's traveling through matter, but a wave is not itself matter. Now, there's a term you need to know, and that's called the wave medium. This is the matter that the wave travels through. Looks like I have a typo here. The matter that the wave travels through. We call that the wave medium. So for some kinds of waves, and we'll talk about some different kinds, the energy of the wave is traveling through the medium. For other kinds of waves, no medium is required at all. It can travel through empty space. Now, one of the things that I want you to understand are the parts of a wave. Waves have parts that have different names, and so we're talking about some vocabulary here. If you could look at a wave, a simple wave like this, that you've probably seen something like this before, which just kind of goes up and down. If you could stop it while it's in motion, you could identify its parts. So here are the parts, and my suggestion is when you're writing your notes, that you go ahead and draw this as part of your notes. So right now you may have a definition of what a wave is written down, and again, I neglected to say this already, I apologize, but you should be just taking normal Cornell style notes for this one, and the page number is 19, so I apologize, I forgot to say that at the start, but in your notes right now, probably the best thing to do is just to go ahead and draw this wave. You may not need to draw the entire thing, maybe just 2 bumps, but some of the terms that you need to know, let's start with the crest of the wave. This is what we call the highest point of the wave. We're going to look at some different kinds of waves, but the crest is always sort of the tallest part of the wave. The opposite of that is the wave trough. It's spelled kind of strange, but that's how you pronounce that. It's the trough. Think of like a feeding trough for animals or something like that. And that's going to be the lowest part of the wave, the lowest point on the wave. And then another term you need to know is the wave amplitude. The wave amplitude is it's pretty much half the distance between the trough and the crest. It's half of that distance. And it's actually defined as the distance between this dotted line right here and either the crest or the trough. And that dotted line is the rest position. So the distance between the rest position and the crest or the trough is known as the amplitude of the wave. The other part you need to know is the wavelength. And the wavelength is defined as the distance between any 2 points on adjacent waves. So you have distance between crest and crest of 2 waves, distance between trough and trough on 2 waves, distance between pretty much any point on the wave, and that same point on the next wave. So here it is again. We have the highest point on the wave is the crest, the lowest point is the trough. The dotted line running down the center here is known as the rest position. Here again is the wave amplitude. The amplitude of the wave is the distance or height from the crest to the rest position, or even from the trough, this low point, to the rest position. Okay, so either this distance here or this distance here. And it doesn't really matter how you define it. Most people define it as the distance between the crest and the rest position, but you can define it either way. One thing you do need to know is that waves that have a greater amplitude are actually carrying more energy. So this distance, if it goes up higher, that's going to have more energy. And if it's lower, it has less energy. And again, the wavelength of the wave is the distance from crest to crest or from trough to trough. And you can see it's marked out here on this diagram 3 different ways. You go from the crest to the crest of one wave to the crest of the next, or from some midpoint to that same point on the next wave, or even from trough to trough here. Any one of those, it's the same distance if you actually look at it, and you could even measure it. It's the same distance on this diagram. Okay, and one more thing you need to know about waves and terminology associated with waves is wave frequency. And the definition of wave frequency is it's the number of waves that pass a certain point every second. So it's measured as something happening per second. The units are CPS, cycles per second, or you've probably heard this term, hertz. Hz stands for hertz, and hertz means cycles per second. So those are the 2 units we might use for frequency. And the thing you need to know is that frequency and wavelength have what's called an inverse relationship. As one goes up, the other goes down. So if you have a greater frequency, greater cycles per second, or waves passing by per second, then that means the wavelength is short. If you have a longer frequency, so the waves are coming by less often, less per second, then the wavelength is going to be longer. So one way to look at that is like this diagram, which I like. This top wave shows a high frequency wave, so lots of these crests going by every second. And if you look at the wavelength, it's not very long. Compare that to this low frequency wave at the bottom, you see not as many crests going by every second, and you see the wavelength comparatively is longer. Now, something that I thought would be really interesting for you to look at is this website that I have on here. It's a really long URL, and I apologize for that, but I couldn't figure out another way to get you there without typing in the whole thing. But here's the question. What kind of wave would make you the most nauseated if you were on a boat on the sea? I guess I came up with this question because I had recently taken a cruise, but it's a really neat website. You can go in there and you can put in your wave, your frequency, and your amplitude, and you can get a look at what the wave looks like with a boat on the ocean. So take a look at that. Okay, the last thing I want to talk about is 2 different types of waves, and we're going to spend a little bit of time in class going back over this, but if you're using headings in your left column on your Cornell notes, you could put the terms on the left side if you want to. But a transverse wave is defined as a wave in which the particles that are carrying the wave, so in other words the medium, the particles are actually moving perpendicular or up and down compared to the direction that the wave is moving. Okay, so if you look at this rope, this is just a fellow holding a rope, and it's tied to the wall here. And if he moves his hand up and down, which is indicated here, then you get a wave that looks like the one shown. Another example of this kind of wave would be, if you think about the wave at a football game. People are standing up and down, but the wave isn't going up and down. The wave is going around the stadium. So if you're at a football game or something like that, the wave is going around. So the energy of the wave is moving one direction, but the actual people that are carrying the wave, they're standing up and standing down. So the particles in the medium, or in other words, what's carrying the wave, is moving perpendicular, so at a different in a different direction than the actual wave energy is going. An example of this type of wave, light waves. The second type of wave that I want you to know about is called a longitudinal wave. Sometimes it's called a compressional wave. And in a longitudinal wave, the particles of the medium, in other words, the particles that are carrying the wave, are moving parallel or the same direction that the wave is moving. So the wave energy is the same direction that the particles are moving back and forth. In this example, again, you have something, I'm not sure what this is supposed to be, I think maybe a spring, but it's attached to the wall here. And look at the direction that the hand is moving to make the spring jiggle. It's moving back and forth instead of up and down. So, in fact, the wave is going toward the wall, and the particles that make up the wave, or the thing that's carrying the wave energy, is also moving that direction. So that's a longitudinal wave. An example of this are sound waves. This is how sound waves travel. Another example, and we're going to experience this in class, is the wave that travels through a slinky when you move a spring. That's an example of a longitudinal wave. Now, longitudinal waves are a little bit different than transverse waves. We've talked about wavelength and amplitude and crests and troughs, and most of that has to do with transverse waves. Longitudinal waves are a little bit different. They don't have a crest and a trough. Instead, they have something called compressions, and they have something called rarefactions. And these are areas where, in compressions, the particles are pressed together, because remember, it's jiggling back and forth instead of moving up and down to carry the wave energy. So in the compressions, the particles are squeezed together, and you can see this down below is a slinky. And for the compressions, you see the slinky rings, or the spring is actually squeezed together. In the rarefactions, the particles are spread out. So you can see in this diagram, the rarefaction is the area where the slinky is actually kind of spreading out, spreading apart. And of course, the wave itself is moving that direction. I suppose it could be moving the other direction too, but the slinky is squeezing together and spreading out, squeezing together and spreading out. And that's how the wave is carried along the slinky. Okay, so that's all I had for this lesson. This is going, remember, on page 19 in your notebook, and you can write your notes just Cornell style, ordinary Cornell style notes. Make sure you do your summary at the bottom of page 19. And I guess that's all I had to say.
Made with Doodlecast Pro.